Ben bir mühendisim. Ofiste, evde, yaşamın her alanındayım. Görülmeyen ama hissedilenim. Ben ne kadar görünmez olursam, projelerim o kadar başarıyla tasarlanmış ve uygulanmış demektir. Tıpkı sizi sizden fazla düşünen gizli bir kahraman gibi. Kahramanlık, kağıtla kalem bir araya geldiğinde geleceğe yön verebilecek kadar cesur olmaktır. Çünkü mühendislik, bilim ve doğa alanında tüm bilinenleri yine doğa ve insanlık için kullanmaktır. Tasarımda sadece estetiğin değil, sürdürülebilirlik, enerji verimliliği, çevre duyarlılığı gibi kavramların da altını çizmektir. Mühendislik, modern, konforlu ve doğaya saygı gösteren yenilikçi yaşam alanlarını hayal etmek ve gerçeğe dönüştürmektir. Gelecek kuşaklara yön vermektir. Binlerce yıl önce bir kıvılcımla yaratılan aydınlığı bugün tek bir tuşla milyonlarca insanın yaşadığı yerlere taşımaktır. Geceyi gündüze, soğuğu sıcağa, sıcağı soğuğa çevirebilmektir. İnsanlığın ihtiyaçlarını karşılamak için hayallerimizi gerçekleştirirken yanımızda TTMD vardı. 1992 yılında kurulduğundan bu yana çatısı altında güven bulduğumuz, etik değerlerin teşkili ve temel sorunların çözümü için birlikte çalıştığımız yol arkadaşımız. Farklı disiplinlerden gelen profesyonellerin ortak amaçlar için toplandığı TTMD, üyeler arasında iletişim ve tartışma ortamı yaratıyor, bilimsel ve teknolojik yayınlar yapıyor, üniversite, sanayi, işbirliğine destek veriyor, çevreci ve enerji verimli çözümlerin yaygınlaşmasını destekliyor, yurt dışındaki gelişmeleri izliyor ve sektörü yurt dışında temsil ediyor. Bizler tüm insanlığın iyi yaşam arayışına çözüm buluyoruz. Bizler yarınlarımızı şimdiden kuruyor ve daha sürdürülebilir bir dünya için çalışıyoruz. TTM'de 1992'den bugüne yaşam mekanlarında insanlığın konfor ihtiyaçlarını doğaya saygı göstererek sağlamak için var. Mühendislik mesleğini etik değerler doğrultusunda uygulamak için var. Türk Tesisat Mühendisleri Derneği. Gelin geleceği birlikte yaratalım.
Good morning, ladies and gentlemen. It's my pleasure to welcome you and also to moderate this webinar organized by TTMD, Turkish HVAC Association. And it's a great pleasure to welcome all of you to this webinar. I am Halime Paksoy, a chemical engineer working at Çukurova University Chemistry Department as professor and also the director for Center for Environmental Research. Before we start our webinar, I would like to give you brief information on International Energy Agency and technology collaboration programs, which we are collaborating in organization of this webinar. International Energy Agency was founded in 1974 for long-term cooperation on energy R&D. At the beginning, it was mainly on energy security for sustainable supplies of oil. And recently, it's more on alternative energy sources of energy conservation measures with the main focus on climate crisis. Over 80 technology collaboration programs called TCPs in short have been created over the years, almost in 5 decades of technology collaboration with all stakeholders, including research, industry, policymakers, NGOs, and all institutions. Today, there are 39 TCPs with representatives from 55 countries, around 300 institutions, and with global network of thousands of experts. This is a unique network with so many experts working together. TTMD represents Turkey in 3 of these TCPs: energy storage, solar heating and cooling, and energy in buildings and communities. Next slide, please. Energy storage contributes to the transition toward a renewable energy system by the use of any kind of energy storage through joint research, design, and development since 1978, so almost from the beginning of IEA. And currently there are 21 members. We can see the website and LinkedIn address there. And the solar heating and cooling program of International Energy was established around the same years, 1977, to promote the use of all aspects of solar thermal energy, with 28 members today and 9 current solar projects. So these are the two TCPs we are collaborating in organizing today's webinar. And now I would like to start webinar with introductory information. We will talk about energy storage here. Energy storage is a hidden gem, and it has enormous potential benefits that makes transition to the zero energy future, zero carbon future. Storages may vary in types and sizes, and the ultimate goal is using renewables more efficiently and in more affordable ways. Today, our subject is large energy storages, thermal energy storages. As opposed to small ones, large can be beautiful and economical. We will hear much more from our distinguished speaker, Dr. Wim van Helden from AEE Institute for Sustainable Technologies in Austria. Title of his presentation is Large Thermal Energy Storage for District Heating. They just have finished task 39 under his leadership on this topic and is getting ready to start a new one. Before I give stage to Dr. Helden, I would like to ask you to use the chat for your questions. You can write them during or after the presentation. We will answer them after the presentation is completed. So, Dr. Helden, the floor is yours now. Could you please start by introducing yourself first?
Thank you, Halime. Yes, I'm Wim van Helden. I'm working at AEE Intec. It's an Austrian-based research and development institute. AEE Intec is working on sustainable technologies and the better use of resources. And within AEE Intec, since 2014, I'm working on thermal energy storage. Not only the large energy storages that you will hear about today, but also compact thermal energy storages. I'm also active in the European Renewable Heating and Cooling Technology and Innovation Platform, and also for the scientific committee of the International Renewable Energy Storage Conference that is organized in Germany every year. So I'll show the presentation. Can you see properly now?
Yes, Wim, you can go on.
Okay, thank you. So today's presentation, you will hear more about large thermal energy storages for district heating. It's the current task 39 of the energy storage program of the IEA. And within this work, we work on thermal storage. First, an overview that I borrowed from Andreas Hauer, ZAE Bayern, on the different forms of energy storage. To the left, you can see the storages for electrical energy. In the middle, chemical energy storage, and to the right, storage of thermal energy. And these thermal energy as heat can be stored in different ways, either sensible, latent, or thermochemical. Let us have a look more into detail on the energy storage technologies for thermal energy. First, we have sensible heat, in which the heat is stored in the heat capacity of a substance. You can use for that reservoirs like water pits or aquifers or the ground or soil or even other materials to store the heat. The principle here is that if you store more heat, then the temperature of the substance goes up. So that is why there is a straight line here in the picture to the right. Increasing the enthalpy is combined with increased temperature. Then we have latent heat, in which the most of the heat is stored in a phase change. It can be either melting but also evaporation of a substance. Water can be used, so the very much used ice to liquid water transfer has been used widely. And then also organic and inorganic PCMs are on the market for phase change thermal storage. The third class is sorption heat and chemical heat. We call it thermochemical materials. It can be either a physical principle in which molecules adhere to a surface or to each other in liquids, or a chemical bond with a chemical reaction or a redox reaction. We call the latter two classes compact thermal energy, but for large thermal energy storages, we will look at the principle of sensible heat. So mostly it will be water or sand that is used for storing heat. So we address four basic latent heat storage technologies in task 39. You see here four pictures of the different technologies. On the left top side, it's tank thermal energy storage, or TTES. It's a tank, either concrete or steel, in which water is contained, and this water is then heated up to store the energy. The second one on the right top is the pit thermal energy storage, or PTES. The pit thermal energy storage is a pit, a hole dug in the ground, and then the earth that is dug out of the ground is being used to create the sidewalls. And then everything is topped with an insulating top layer. And then there's devices, inlet and outlet devices to exchange the water with the heat exchanger connected to the system. Then we have aquifer thermal energy storage on the right bottom. This is using ground layers underneath the ground that can carry water and that are confined between a lower and an upper layer that don't let through the water. So the water is confined in this layer. Then we have two wells, a cold well and a hot well, and the water is then transported between the two wells underground. Mostly the temperatures for aquifer thermal energy storage are up to, say, 40 to 45 degrees, but now at the moment there are already also experiments with 85 degrees storage. Then the last category of technologies that we look at in task 39 is to the left bottom. It's the borehole thermal energy storage. And this is a set of vertical pipes that have been drilled into the ground, through which heat transfer fluid is transported. And this heat transfer fluid gives the heat to the ground or takes the heat from the ground when you want to discharge the storage. So we look at water or soil, and the large thermal energy storage are applied either in district heating or in industries. Depending on the application, it's either a seasonal storage or a weekly or daily storage, and also combined storage strategies are used, being then a multifunctional storage. And the destination that we are developing and doing in task 39 is targeted to decision makers in policy areas, at municipalities, in utilities, and in district heating companies. What is our definition of large? When talking about large, we talk about 1 gigawatt hour per year, meaning that if you have a seasonal storage, it will be a large storage that has this discharge and charge one time per year. If you have a weekly storage, then it will be a smaller storage, say about 30,000 cubic meters or so, that will discharge 50 times. And another aspect of the scope is that the stored heat should be suited for discharging into district heating networks, so of temperatures between 50 and 100 degrees roughly. Why do we need large thermal energy storages? Because energy storages can provide flexibility, and they enable a large uptake of renewable heat sources, sources that have a great variation throughout the year. Examples of the last two are, for instance, solar thermal heat and deep geothermal heat, but a large thermal energy storage also can be used for power to heat in times where electricity is very cheap, that this electricity from wind turbines or PV panels or other renewable sources is stored sustainably in an LTES through a combination of a heat pump or directly. And then, of course, there are other sources for the LTES storage, biomass, CHP, centralized or decentralized, or industrial waste heat, or large heat pump installations in industry. What is the potential of pit thermal energy storage for district heating in Europe? For a European project, we did a first estimate of the potential in Europe. The basis for that was that in 2018, there was a total final energy consumption through district heating systems of 440 terawatt hours. If we assume that 40% of the needed storage technologies are pit thermal energy storage, and that 30% of the annual heat sales should be stored in the storage to be used in winter, for instance, and that presently we would need then a pit thermal energy storage capacity for district heating of about 54,000 gigawatt hours, meaning 54 terawatt hours. This, if we assume that there is a fourfold growth of district heating until 2050, which is also most of the plans of the national policies, then we would arrive in 2050 at about 220,000 gigawatt hours, meaning that there will be an exponential growth of the pit thermal energy storage systems in Europe. You will see more about this later in the presentation. So what is working in IEA tasks all about? It's working together with experts all around the world. These experts collaborate on a common work plan. So we have a work plan that work is being done by the experts, but all experts have to bring their own funding, meaning that there's no central funding for the projects, but it's decentralized through national or international funding of the experts. So starting with the work plan, we started the kickoff of the task 39 in October 2020. Then every 6 months we had an expert meeting. Because of COVID, the first 3 were online, and we had a first physical meeting in Graz in 2022. There were 2 meetings that were connected to a technical tour to a pit thermal energy storage installation. You see here the visit to Dronninglund, a photograph of the group standing on top of the pit thermal energy storage. And this was a pit thermal energy storage that had a renovated lid, so the top that we are standing on was brand new. Half a year later, we went to Hamburg in Germany, and north of Hamburg in the city of Meldorf, a new pit thermal energy storage is being built. And at that time, you can see that still the water is only in the pit, and the lid at that moment, the insulating cover, was being constructed. The work in the task is subdivided into 4 subtasks. We have a subtask on application scenarios, assessment of concepts and integration aspects. Then we have a subtask B on components and materials database, a subtask C on the round-robin numerical simulation of thermal energy storages, and the last subtask D, in which we work on developing knowledge and disseminate it to decision makers. In the next 4 slides, you will see some of the results of the task. The task is almost ended, and most of the deliverables will become available in this next month. If we look into subtask A, it's also working on a key performance indicators list. And we define key performance indicator in order to have a better view on the quality and the challenges and barriers connected to different heat storage technologies. We split the KPIs in 3 categories. The first category is the technical one. So for instance, what is the power for charging and discharging? What is the efficiency of the storage over certain periods? What is the exegetic efficiency, for instance, in the mix number, and other technical performance indicators. Then we also look at economic performance indicator, for instance, the investment cost, the financing cost, but also the levelized cost of energy storage. So what does a kilowatt hour of stored energy cost to the end user? And then, of course, CAPEX, OPEX, and marginal cost are also key performance indicators of the thermal energy storage. And the third category is the environmental performance indicators. But the problem here is that they do not always include a clear definition or a protocol for the measurement. So this is one of the challenges also for the group, also for the follow-up, in order to come up with clear protocols how to define environmental performance indicators. Then we have subtask B on materials database and material test. One of the aspects is that we work on a database, and what we have structured now is that we have 3 technologies from which you can select. It's the pit storage, the borehole storage, and the aquifer storage. And from these storages, you can select a component. Here, the example is a component of the pit storage. And these components for the pit storage are either soil, protection, tightness, the water, and the thermal insulation. And here we chose the soil, and from the soil you can choose the different types of soil. And then from this different type, can find the different thermal properties or also structural properties of this element. With this, we have a database that will enable engineers to make a proper modeling of the different aspects of a thermal energy storage. Then we have subtask C on round-robin simulation. What we there did is we had a large group of experts that are calculating the performance of large thermal energy storage, and we divided the group into 7 applications. So there's one application for underground tank thermal energy storage with 100,000 cubic meter water volume. The other one is the above ground tank. It's a steel tank with 50,000 cubic meters. Then there's a pit thermal energy storage with a conical form, and a pit thermal energy with a pyramidical form. And then there's one aquifer thermal energy storage and one borehole thermal energy storage. And the idea is that all the experts with their software simulate a year of charging and discharging the storage is in a seasonal setting. So 3 months charging, 1 month waiting, and then 3 months discharging. And this is a so-called simplified load profile. And then the experts compare to each other the results of the calculation and try to find out where the difference come from and make the protocol of the simulation and the values of the boundary conditions in such a way that the outcomes of the different software is as identical as possible. Then we have subtask D, working on knowledge base for decision makers. We introduced leaflets. They are almost ready with information material. You will see more examples of these leaflets soon. And then we have the Task 39 webinar, this one for instance, and we have policy workshops, one on the 5th of December. It will be an online workshop with the question, are large thermal energy storages a key element of the future energy system? The form of the workshop is as follows. We have a panel of national energy agencies that will give a short introduction of their view on large thermal energy storages, and also the European Commission. And we have task 39 experts explaining about the technologies and the barriers. And then we have discussion on the different topics that, for instance, barriers that need to be resolved in order to enable an uptake of large thermal energy storages in Europe. This could be legislation or permitting procedures or financing. So let's have a look at some examples of leaflets. The first example is a use case of a tank thermal energy storage. This one is built by Vattenfall in Berlin. It's 50,000 cubic meter storage. You can see it here by the person standing here in the right lower corner of the storage. It's a steel tank, and the steel tank is used to make the district heating network of Berlin more flexible. Another example is also perhaps very valid and very important for Turkey. It's aquifer thermal energy storage, and in this case it will be applied to a greenhouse. And here the aquifer thermal energy storage is combined with a geothermal well. So left you can see the different elements of and phases of the aquifer thermal energy storage. So it's drilling, it's installing the wellheads, then it's the electrical pumps installation, and then what remains on top is this installation in which the pumps and the pipes are the only thing visible on top. Then we have two wells, one cold well and one hot well, and one third well was used for monitoring. Because this is a pilot project in the Netherlands in which also some relevant development and research questions have been defined, and therefore the installation is monitored for a number of years. The next slide will show the use case for this one. It's a greenhouse in which peppers are being grown, and the idea is that the heat normally is coming from a very deep geothermal heat well. It produces heat at 90 degrees centigrade from a depth of 2,400 meters. If a geothermal well is only profitable if it is used throughout the year with a constant power. So if there are times in summer that this heat is not needed directly, then the heat is being stored in a high temperature aquifer thermal energy storage. So the combination of geothermal and an aquifer thermal energy storage makes it possible that the geothermal source can provide heat all over the year for this greenhouse. So the end, as you heard, of task 39 is at the end of the year. It was a 3-year task, but it will be followed up by the so-called task 45, in which we had a slight change of the focus of the work. The new work will be focused on accelerating the uptake of large thermal energy storages. And the idea is that because a lot of district heating companies now have the policy of increasing the district heating system and also increasing the renewable sources in order to be less dependent on natural gas, for instance, they need to have a large thermal energy storage. And this is why we, together with different stakeholders, would like to work on, bringing down the barriers and the challenges of the market uptake of large thermal energy storages. The new task will have a 4-year duration and will start 1st of January. And already 22 organizations from 7 countries have indicated that they will collaborate with us in the task 45. And of course, also experts and interested people from the from the Turkey are invited to contact me if they are interested in collaborating. A few slides now more on pit thermal energy storage. This is an example of a pit thermal energy storage. It's the biggest until now. It's in Vojens in Denmark. Here in the picture it's still empty. It will be filled with water, or it was filled with water in 2014. And it has a volume of 200,000 square meters. And in the bottom of the picture, the right bottom, you can see the solar thermal field that is connected to this pit thermal energy storage. Here in Vojens, in Denmark, most of the energy is coming from the sun, and this is stored in summer in the storage and will be used by the district heating in winter. Then we have a new project. It is led by AE Intec. It's the Treasure project, and it's all about demonstrating and accelerating the uptake of pit thermal energy storage. Throughout Europe, we have 7 demonstrators indicated here by the red brownish squares. There's 2 in Germany, there are 2 in Poland, there's 1 in Austria, 1 in Serbia, and 1 in France. And as you can see, the volumes of the different storages indicated by the area of the square are different, but also the stage in which the development of the storage is different. For instance, Hechingen already is working on the building of the storage, and it will be ready at the end of 2024, and we will have 3 years of measurement in Hechingen. And we have 1 reference storage in Hoye Tastrup, which is installed and ready this year, and has a monitoring project and program that we can use to make references for our new demonstrators. Next to the 7 demonstrators, we have 15 satellite initiatives. These are plans for district heating companies that would like to have a pit thermal energy storage, but these are only early plans, and they will have workshops together with the demonstrators in our project in order to accelerate the exchange of information and to bring down the time needed between the first idea and the operation of a pit thermal energy storage. A last slide about the cost of large thermal energy storage. And one very important aspect is that if you have a higher volume that you can store, then the cost will be lower. And this is because the specific heat losses decrease due to the shrinking surface to volume ratio. So the amount of heat that is being stored is proportional to the volume, while the losses are proportional to the surface area around this volume. So a bigger volume leads to a lower specific heat loss, meaning also that the costs of the heat storage will then be lower per cubic meter. Here you see on the x-axis the volume of the different thermal energy storages in water equivalent cubic meters, and it's a logarithmic scale. And on the y-axis you see the cost, the specific heat storage costs for in euro per cubic meter of water equivalent storage capacity. And then you can see that for tank thermal energy storage, you see a line going down here. The highest one here in the picture is Friedrichshafen, but you saw already also a picture of the storage in Berlin that had a volume of 50,000 cubic meters. So that would be around here. If we go to pit thermal energy storage, these are the diamonds, then you see that the price can go from 200 euro per cubic meters for a few thousand cubic meters storage down to Vojens that we saw, the biggest one, 200,000 cubic meter, which has a specific investment cost of about 28 euro per cubic meter water equivalent. Meaning that the higher we go in volume, the more profitable are the cost of thermal energy storages. This brings me to the last slide of the presentation, references. You can see here different links to the IEA website, a link to an Austrian national project, GigaTest, that more or less had first investments on what the requirements are of making a pit thermal energy storage in Central Europe. And then also a link to the policy workshop that will be organized the 5th of December. And if you need more information, you're welcome to contact me. My email is down here. Thank you for your attention.
Thank you very much, Wim. Very interesting presentation showing large is beautiful. Thank you. So, dear participants of our webinar, we are now at the question and answers session. Please, if you have any questions, enter them on the chat on our webinar site. I can start with a question while the others are coming. The last figure you have shown on the cost, investment cost per cubic meter, would you have a similar figure for kilowatt hour, for example, to compare with other storages other than thermal energy, maybe?
Yes, I guess that what you could roughly do is say that we have a temperature difference of about, say, 50 degrees that we can store in a thermal energy storage. And then it would be around, say, 60 kilowatt hours per cubic meter, meaning that you would have to divide the euro per cubic meter water with 60, meaning that for this Voyant storage, we had 28 euro per cubic meter, then it would be, say, 30 divided by 60, so 5 euro cent, something like that.
And that is the cheapest energy I have heard.
Yes. Yeah. No, we have to use another constant in that, because these are the investment costs per capacity. So then you would have to compare with the investment cost of batteries in capacity. And the battery cost per kilowatt hour are still in the several tens of euros per kilowatt hour.
Yeah. And
So it's you could roughly say it's a factor 100 cheaper than electricity storage.
and especially for the pumped hydros that use quite large storage capacities, this could be a significant difference.
Yes.
Okay. Still no questions. And how about these large aquifer thermal energy storage for higher temperature? I knew that aquifer thermal energy storages in the past could be applied until 40 degrees Celsius or so. The
Indeed.
ones you have shown goes up to 85 degrees, some of them. So
Yes.
what are the new things that make them applicable at these temperatures?
Yes. It's an experiment in the sense that up to now it was not permitted to have higher temperatures in the underground. There are two things that have been done. One is that this aquifer are on a higher depth, so about between 300 and 500 meters depth. And it's also an experiment, so this is why the monitoring is. The idea is that this experiment is to find out whether there are chemical or biological effects of this higher temperature in the soil itself. And monitoring this these effects will lead to the conclusion, if there are no effects that are being seen, that the permitting can be expanded to higher temperatures for these kind of systems.
Yeah, so that's an important development that would allow different applications.
Yes, indeed. The number of applications will go up exponentially, because up until 40 degrees you would need a heat pump in order to make tap water. You can only use it for room heating. But if you can store it up to 90 degrees or 85 degrees, then you can use direct heating with the stored heat.
Okay. There are some questions from our participants. The first one, after the earthquake, some airports in Turkey will be re-established, and do you see any potential there?
Yes. Also, aquifer storage, for instance, is used in the airport of Berlin, for instance. As you see, how to say, the footprint that is needed for aquathermal energy storage is very low. What is being done is that a borehole is drilled, and then it's underground. It's going more horizontal to have a large spread out of land area that is being used. But at the top, at the surface, you only see one small, say, technical house that is being used for pumps and for the pipes. And so for airports, for heating, but also for air conditioning, for cooling, aquifer thermal energy would be ideal.
Thank you. And that brings me the question to my mind. Earthquakes, how would they affect the large underground installations like thermal energy storage? Is that something considered at all?
No, that's not to my knowledge yet. I guess that for aquifers, it would be the same with like with oil drilling or gas drilling pipes, because it's a pipe that's being drilled in the underground. And for pit thermal energy storage, for instance, or for tanks, it would have to comply to the same engineering rules as other structures that are being built. But I'm not aware of separate rules or engineering, how do you say, correlations for pit thermal energies with relation to earthquake, how do you say, earthquake aspects.
Thank you. One more question about the precise cost for thermal kilowatt hours, euros
Yep.
per thermal kilowatt hours.
Yes. The picture that you saw, and will also be distributed, this slide, is the investment cost per cubic meter of water, meaning that this is the cost of the storage to be built. And then it will depend on how many kilowatt hours you would store per year per cubic meter of storage volume. So if you would have an industrial system in which there is, say, storage needed every weekend or so, then this storage would be charged and discharged 50 times per year. So there the kilowatt hour cost would be much less than if you had a seasonal storage, for instance, with a solar thermal system, in which there is a charge and discharge only one time per year. So in between the kilowatt hour cost and the cost per investment cost per cubic meter is the number of charges and discharges and the number of the years of the lifetime of the installation.
Thank you. Another question is, how much of total heat demand could be covered with large thermal storage?
Yeah, it can go up to 100%. So there are examples of smaller towns where the heat for district heating is only provided by solar thermal, meaning that in summer there will be some energy needed for hot tap water, but not for room heating. And in winter, all the room heating will be supplied by the storage, by the stored heat in the thermal energy storage. So it can go up to 100%.
And about the barriers, what are the main challenges for getting large thermal heating projects off the ground? More technological costs or rather regulatory?
I would say that the main aspects would be regulatory and financial. So getting things organized, getting the money, and then making the project. But if you go more to Central Europe, then there's less experience in building such a storage. And this is also why we started the Gigatest project. In Denmark, the requirements or the boundary conditions for having a pit thermal energy storage, for instance, are very good because the groundwater is very low. But in other countries, the groundwater level is much higher, which means that you need to have other building technologies, other building techniques in order to be able to build such a construction. And because the construction, if you would like to have a 100,000 cubic meter storage, it's quite expensive. You cannot do experiments with that. So you need to have first projects with smaller storages in order to find your way into building technology, and then gradually go towards the bigger volume storage. And this is something that we that we have planned to address in the Treasure project also. So working on the technology barriers, but also on the permitting and the financing aspects.
Thank you. We have a question from Technical University of Denmark. It's about pit storage and has two sub questions. How does Wim's team manage the heat loss from the stored energy medium, e.g. water, to the ground? And the following questions is, we have a maximum storage temperature limit of nearly 30 degrees in Denmark. This is an official regulation. Do they have similar regulations in other demonstration areas?
Yeah, the first one about the heat loss. The heat losses will be present, and you can only prevent the heat losses when insulating the thermal storage. At the moment, the practice is that only the top lid is insulated, and we are doing some calculations, or people are doing calculations, whether it would be profitable also to have, for instance, the first 5 to 10 meters of the height of the storage, because most of the hot water will be in the top, to also insulate the walls at this highest region. It will, in the end, it will be a matter of cost. So if you have an extra loss of 1 kilowatt hour, whether this cost of this extra kilowatt hour is balancing the extra cost of having insulation in your storage. And then the other question about the maximum temperature. I'm not aware of a maximum temperature of 30 degrees. The maximum temperatures that we are in contact with, and this is for all technologies, is the maximum allowable temperature for groundwater. So the groundwater protection is mostly that you either have a maximum increase of the groundwater temperature or a maximum absolute groundwater temperature. And for Austria, for instance, this latter one is applicable. So in Austria, it's the maximum temperature of the groundwater should not exceed 20 degrees centigrade for the nearest groundwater pit in the region around pit thermal energy storage. So that's something that also with the numerical calculations have to be designed properly.
Thank you. Another question on cost, relative cost of large thermal energy storage, A-TESS, B-TESS, and P-TESS, I think.
I don't have these numbers now at hand. The tank thermal energy storage has up to, say, 50,000 cubic meters, the lowest cost, but that's also the more or less the maximum size that you could build with a tank that has, say, 90 degrees water inside. And then for the higher volumes at the moment, I guess that aquifer thermal energy storage is less expensive than pit thermal energy storage. But at the moment, I cannot give numbers on that.
Okay, thank you. Another question is the main barriers you see for the large deployment of these technologies in Europe, in France, for example.
In France, yeah. I know that the legislation and permitting in France is not well developed. So that's one thing. And another barrier is that thermal energy storage is not well known. So it's if people talk about energy storage in general, then it's electricity storage, then it's the storage of electricity for the electricity grid. So that would also be a barrier in France.
Yeah, we have a similar situation in Turkey too.
Yeah.
Another question is there any new solutions in areas where land is scarce for large-scale seasonal storage, water storage?
Yeah. What we are looking into, we also did some work in GigaTest, is that if you have a pit thermal energy storage, the lid until now is only walkable. So you can stand on the lid, but you cannot do anything on the lid. And the idea is that for future projects, we make the lid in such a way that, for instance, a greenhouse can be put on it, or a park, or water houses, or a pond, so that the area that has been used to build this pit thermal energy storage below it still can be used in an urban environment. And this is also because if you go nearer to a city, then the price of a square meter of area is much higher than if you have rural areas.
Another question on life cycle assessments. Have you done any LCAs on these systems?
Not yet, but it's being part of the new Treasure project. So what we will do there is look into the LCA of the different components that are needed for the different technologies, and then make a calculation of the life cycle aspects of the pit thermal energy storage.
Okay, thank you very much. I think we have answered all the questions. Let me.
They were great questions. Yeah, thank you.
Yes, thank you, Wim, for this very interesting presentation. And I think especially in Turkey, where we have this lots of solar energy and space available, we need large thermal energy storage projects. And
Definitely, yes. Yeah.
yeah, one application like Professor Çakan from Technical University of Istanbul asked could be airports, but greenhouses I also think is very important. We already have some geothermal district heating in Turkey. These are some areas we can look into. And of course, we may need some legislative barriers that we have to overcome first.
Yeah.
Yes.
Yes, definitely. And as I said in my presentation, experts from Turkey are very welcome to contact me if they are interested. And if they would like to participate also in the new task 45, they are very welcome.
Thank you. Yes, so we have a number of Turkish experts in the webinar now, either them or anyone they know, or we will, of course, send in information to all the TTMD network about your
Great.
new task. Yes. So if there are no more questions, I would like to thank Wim for this very nice presentation and
Welcome.
giving us the chance to have this together, and thank all the participants for their questions and joining us in this webinar. We will have the presentation in PDF form available for all the participants. There are questions about that too. So goodbye. Thank you.
Thank you. Bye-bye.